Okay, so last time we talked about what?
Stokes vector.
Stokes vectors. And what are Stokes vectors good for? Partially polarized or unpolarized or fully polarized.
Yeah.
You can handle anything with them. So if you have completely polarized light, would you rather use a Jones vector or a Stokes vector? Why?
That's simpler.
It's easier. Yeah, for sure. Okay. So we also looked at the fact that if you start with completely unpolarized light, it's pretty trivial to get fully polarized light if you're willing to throw away half the power. So, not a big deal. We also looked at the Poincare sphere and saw that the Euler vectors encompass the interior of the sphere as well as the exterior. Jones vectors, you can only deal with the exterior of the sphere. Okay, so do you think we've talked about polarization enough?
I don't know, have we?
Well, I'm interested in your opinion.
There's no way there's something more.
Turns out there's a lot more. But we're not going to talk about it. We've learned enough for our purposes. So you should all be pretty expert with polarization now. You should understand what it is, how to describe it in a myriad of different ways, how to go between the different representations, and you should understand how to manipulate polarization. What's the name of the game in manipulating it? Wave plates. Wave plates are where it's at. Yeah. So quarter wave plates, half wave plates. And if you ever have partially polarized light or unpolarized light, now you understand that, you know what to do with it. Okay, so
Does polarization change at all when we're talking about like these different models? Like when we listed off all these different models of optics, is polarization kind of constant within all of those?
So short answer is no, in the sense that the scalar models and models based upon the scalar model don't have anything to say about polarization.
It just doesn't exist in that world.
It doesn't exist in that world. And so, because in the real world there is polarization, then those scalar models pertain to a single polarization state. So you're basically assuming everything has the same polarization state and it does not change. And then those models are perfectly fine in that case. So, but if you have a situation where your optical elements or your optical system modifies the polarization state in a way that you care about, then yeah, then you need to use an electromagnetic model or something derived from that. So, we've talked about scalar and electromagnetic models. We've talked about fundamental solutions to the wave equation in both. We've seen that we really like dealing with monochromatic waves, but we can deal with polychromatic. Polychromatic is just a sum of monochromatic waves. We also have seen that that you can look at the bandwidth of light for a polychromatic wave and directly understand temporal coherence. We've looked at the angular size of a source of independent incoherent emitters. We understand now how that affects spatial coherence. And now we've dived into polarization and have gotten that down. So in all of these things, what we've been talking about is propagation in dielectric media, linear, isotropic, homogeneous, non-dispersive dielectric media. And what we want to do now is change that up and look at propagation in a situation where we have two different such media and what happens at the interface between them. So reflection and refraction. And we want to make sure that we've really got this down because it's fundamental to a lot of devices and a lot of phenomena. So that's our next topic, reflection and refraction. So if we set up our problem as having a boundary between two materials, dielectric materials with all those caveats, Therefore, we just have to specify the refractive indices N1 and N2. And let's say that the interface is in the XY plane, such that the surface normal, N hat here, is in the Z direction. Then we want to assume that we're using the electromagnetic model, and we want to assume plane waves. Because if we assume plane waves, as we've noted before, then we can understand pretty much anything else. Okay, so presumably then, we have a plane wave incident on this interface, and so we can represent that plane wave by its wave vector, k sub I. And let's say it's incident at an angle theta sub I with respect to the normal to the surface. Then, in general, we expect to get a reflected wave, kr, at some angle theta r, and a transmitted wave, kt, at some angle theta t. And it turns out, we won't show this, but it's not too bad to show, the incident wave vector ki, the reflected wave vector kr, the transmitted wave vector kt are all in the same plane. And we call that the plane of incidence. And now our job is to answer two questions. The first question is, what directions do the reflected and transmitted wave go? And the second question is, how much of the incident wave is reflected and how much is refracted? And this how much, we can answer it in terms of the fields, electric fields usually, and we could answer it in terms of power. And it's really important to understand the difference between the two, and we'll go through that. Okay, so our first job is to answer these two questions. For an incident plane wave, what's the direction of the reflected and transmitted plane waves? And then how much is reflected and transmitted? How much in terms of the incident field? How much in terms of incident power? Okay, now, because we've assumed the electromagnetic model, what principle are we going to use to answer these questions? Jones vector. Snell's law? Actually, Snell's law is going to be an answer to this. So Snell's law is going to fall out of what we do.
Conservation of energy.
Conservation of energy? Yeah, it turns out that's going to fall out of what we do too. E equals mc squared. Well, maybe if we're doing general relativity or something. But we have a boundary between two materials.
Oh, Maxwell.
Yeah, Maxwell's equations, of course. I mean, electromagnetic model is based on Maxwell's equations. But we have a boundary between two materials, and we have an electromagnetic wave.
Boundary conditions.
Boundary conditions. That's the only thing we can resort to. So we have to apply boundary conditions at this boundary. Now, you probably remember one boundary condition is that the tangential electric field has to be continuous across a boundary. What's a tangential electric field?
Something that goes like this.
Is it this way or that way?
It's in the X direction. Yeah.
Isn't it?
X direction. Tangential means in the plane of the boundary. Yeah. Okay, so So the tangential electric field has to be continuous across the boundary, which means the total electric field on the left side has to be the same as the total electric field on the right side, meaning the tangential components of those two fields. Okay, so if we want to set that up as a condition, we better write down what the incident electric field is, the reflected and the transmitted electric field, so that we can use those to apply the boundary conditions. So let's do that. Let's write down the complex representation of the instant electric field. And what will it be? Remember, it's a plane wave.
Some complex magnitude times e to the j omega t.
So complex magnitude, how do you want me to write it?
E naught.
You not? I'm gonna do I just because we're instant. And is it a scalar or a vector? It's a vector. And then what else?
E to the
E to the J. KZ means propagation in what direction? In the Z direction. And here we're not propagating in the Z direction.
Some sort of cosine.
So we have our time dependence, omega t, and then we have our space dependence, k sub I dot r. Okay. So now let's write down the complex representation of the reflected field. So what's it going to be? Same thing with some different subscripts? So ER, e to the j, and just to be complete, let me subscript this as omega I, omega r, and then we have kr dot r. And then likewise for the transmitted field, complex representation, we have et, e to the j, omega sub t t minus k sub t dot r. Okay.
Those R's aren't necessarily all the same thing, right?
The R's, remember, R is just a position vector. It's just a shorthand for saying some point in space.
So would that be the point at the boundary where the wave is meeting the boundary?
Yes. So if we're talking about a boundary condition, that means we're restricting R to be in the xy plane, meaning on the boundary. Okay, so what we want now is we haven't specified the direction of EI, ER, or ET. What do we know about the direction of those things? What's that?
You know the angle, the incident.
We know the instant angle, but
You mean the direction of that the electric field is, like if it's tangential or?
what's the one fact we have for a plane wave about the direction of the electric field? It's going to be orthogonal to the direction of propagation. So EI is somewhere in this plane, right? And likewise, ER is somewhere in this plane, and ET is somewhere in that plane. So that's all we know, because we haven't specified anything else. And what we want is, for each of these, what's the component of the electric field that's in this plane? So how do we get that? There's an easy way and there's a hard way. Let's do the easy way. The easy way is n hat crossed into EI of RT. What direction is that? That cross product, the result of the cross product, what direction will it be? It's orthogonal to both, right? So your key point is orthogonal to n hat. What's orthogonal to n hat?
It's the interface plane.
Yeah, it's the plane we want. So if we just take the cross product of the electric field with n hat, then we have the tangential component of the field.
And then how is the surface normal?
Surface normal, z direction. So that is the tangential component of the instant electric field. Yeah, Carlos?
No, I'm just doing it in my head, sorry.
Okay.
My pencil's spinning. but-
Okay. All right, so what we need is that the total electric field, total tangential electric field on the left-hand side is equal to the total tangential electric field on the right-hand side. So this is only part of the tangential electric field on the left-hand side. So what else do we need?
We take the cross product with reflected field.
Yep. So we need n hat crossed into e sub r, rt. So that's the total tangential field on the left-hand side in material with refractive index n1. And on the right-hand side, we only have one field, so that's easy. N hat cross e sub t, rt. So that's our boundary condition for the electric field. Now let's substitute in what we've got here for these different pieces of the electric field. So we have n hat crossed into e sub I, e to the j, omega I t, minus k sub I dot r, plus n hat cross e sub r, e to the j, omega sub rt, minus k sub r dot r, and all of that has to be equal to n hat cross e sub t, e to the j, omega t times t minus k sub t dot r. And really, this is not something that has to be true everywhere, it only has to be true on the boundary. So we can take this and say evaluated at z equals 0, and this evaluated at z equals 0. Yeah.
Does the normal stay the same on the other side? So
Yeah, so we're defining it as going from material N1 into material N2. Okay, so this then is our boundary condition on the electric field. Okay, so we look at that and we say, we don't know the direction of EI, ER, or ET, but is there something we can say about the relationships here? And yeah, there is, namely that on this boundary, this has to be true for all times t and all positions r on the boundary. So that means that here in the complex exponentials, if there was a different functional dependence on boundary position or time, then this could never be true. Which means that these have to be equal, or we can never have that equation be true. So we must have that omega it minus k sub I dot r, evaluated at z equals 0, has to be equal to omega sub rt minus k sub r dot r, evaluated at z equals 0, has to be equal to omega sub t minus k sub t dot r, evaluated at z equals 0. That has to be true for all time and all positions on the boundary. Otherwise, this could never be true. Okay, so this relationship here has to be true for all times t, which means that Wi has to be equal to Wr has to be equal to Wt. In other words, there's no frequency change upon reflection or transmission, which we already intuitively probably assumed, but that fact falls out of the boundary conditions. Okay, so that leaves us with k sub I dot r at z equals 0 has to be k sub r dot r, x equals 0, has to be equal to k sub t dot r at z equals 0. Okay. So let's take the first thing here and look at it. What is k sub I? Just looking at our diagram. What's its magnitude going to be?
Magnitude's 1 because it's a propagation vector unallowed k hat.
Right. Now, what's the magnitude of the wave vector? So,
Can say there's some
It's a
cosine
number,
of theta
okay.
r.
k sub I. So I heard a 2 pi over lambda. And let's say that's lambda not in free space, then we multiply by n1, because lambda 1 is going to be lambda naught over n1. Wavelength in medium n1 is wavelength in free space divided by the refractive index. Okay, so that's certainly one form we could use. We could also say omega over c times n1, same thing.
Yeah.
So it's just the wave number. And the wave number is in the Helmholtz equation that we solved to get the wave equation. Okay, so let's use, just for fun, the omega over c in 1. And now what are the components of the wave vector ki? How much of it do we have in the x direction?
Cosine of theta r.
The x direction?
Sine.
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 So this would be x hat sine of theta I. And in the z direction?
Cosine.
Yeah, z hat cosine theta I. Okay, so now what about for the reflected wave vector? Same magnitude, right? Because it's in the same material. And then what about the components?
With x, that will be sine of theta.
And in z is cosine.
And but z is in the negative z direction, right?
Yeah.
So minus z hat cosine theta r. Okay, so now when we do the dot product with this, we end up with, for the left-hand side over here, we have omega over c n1 x sine theta I plus z cosine theta I, and that's going to be evaluated at z equals 0. Has to be equal to omega over c n1 x sine theta r minus z cosine theta r evaluated at z equals 0. Yeah.
Is there another assumption? Because I would assume there would also be a y component in there.
This is just for the wave vector. So you'd be talking about something coming in like this.
Oh, so, okay. So
'Cause-
in the plane of the wave vector then, you're saying this is actually a plane and, yeah, okay.
Yes. Exactly. No, I'm glad you brought that up. So I deliberately set up the problem so that ki was in the xz plane.
Okay.
Yeah. And we could have had it come out of the plane, but then this thing would be going into the board, and this thing would be going into the board. They'd all be coplanar, and then we'd really need to do a coordinate rotation to make things a little nicer for us. But it'd get us to the same situation. Okay, so if we look at this, z is equal to 0, So this term is 0, right? And then omega over Cn1, that's common. And then we're just left with this, and the x is common. So that leaves us with sine of theta I is sine of theta r, or in other words, theta I is theta r, which is the law of reflection. So falls right out of the boundary conditions. And because these are the same, let's change our notation over here and call this theta 1 because we're in material 1. And now we know that is also theta 1. Okay. So now let's take the first and third terms. And here, all we need to do is we need to know what case of t is. So what is case of t? Omega over c
Into
n2. And then what?
sine
Sine of
theta t
theta t.
plus
Plus
z cosine of theta t.
Cosine of theta t. Okay, perfect. So then we do the first term and the third term have to be equal. So we have omega over c and 1 x sine of theta I plus z cosine of theta I. And that's going to be equal to omega over c and 2 x sine of theta t plus z cosine of theta t evaluated at z equal to 0. Okay, so z is equal to 0, so this term is 0, that term 0. Omega over c cancels, but notice the refractive indices are different. And then this term with the x's cancel. So that leaves us with n1 sine of theta I is equal to n2 sine of theta t, which is Snell's law. So Snell's law falls right out of the boundary conditions. And let's do another change of notation. We already said theta I, we're going to call theta 1. Theta t, let's call it theta 2, the angle in material 2. So I can rewrite this then as n1 sine theta 1 is equal to n2 sine theta 2. So that's our Snell's law. Here's our law of reflection, which just means we've got theta 1 for the incident and reflected angles. Okay, so notice we just answered our first question. What directions the reflected and transmitted waves go? And we answered them by only looking at the phase terms in our expression for the boundary condition. And by saying that these things are equal, notice that means these guys cancel out. So now we're just left with these terms, which are basically amplitude terms, and that's how we're going to answer the second question. So, following along? Make sense? Okay. All right. Now, before we go to answering the second question, I want to make a comment and point your attention to the following fact. Notice that here, if we, and I'm going to do this over here, if we multiply back through by omega over c n1 sine of theta 1, notice that that is just the x component of the incident wave vector. That's just this right here. This much. So KIX. And then on this side over here, if we multiply through by omega over CN1, notice that's just KRX. So that's this piece right here, KRX. And then on this side of the equation of Snell's law, if I multiply through by omega over C, then what I have is KTX, which is this right here, KTX. And notice what the law of reflection and the law of refraction are saying is just that, which is what this says, K1x is KRX is KTX. So the x components of the wave vectors are the same, which is the law of reflection and Snell's law together. That's what they're saying. The x components of the wave vectors are the same. Which means I could do the following, and again, I'm trying to leave the right-hand board untouched, so I'm just going to intermingle over here. That if I drew, this is the x direction, but now let's make it, let's make this wave vector space. So this is K space. So this boundary then is the boundary between the two media, and it's going to be the x direction of the wave vector. Then on the left-hand side, I can draw all possible wave vectors that could be incident on this interface as just a circle. And the radius of the circle is just n over omega over c, n1. That's the radius of the circle. And on the right-hand side, I could similarly draw all possible wave vector states, and the radius of that half circle is going to be omega over c times n2. All right? So, what we're saying then is, if I have a wave vector instant at angle theta 1 here, then I can drop a perpendicular over here, and this much is KIX, right? And KIX has to be KRX. So I could draw KIX here for KRX, and drop a perpendicular over here, and then draw in KR. So I can just graphically figure out what direction my reflected wave is. But I could also drop a perpendicular over here and graphically figure out what KT is. Does that make sense?
Mm-hmm.
All operating on the basis of that fact. And that is a wave vector diagram. And how many of you have seen wave vector diagrams? Okay, some of you. So this is where it comes from. Is from the boundary conditions, the fact that the phase terms have to be equal. And then have any of you seen a wave vector diagram where the surface is a diffraction gradient? Okay. So then, in that case, what happens is that you have the initial x component of the k vector, and then you have some grading wave vector, call it capital K, and then what you end up with is that you get the reflected wave vector plus integer multiples of that in that direction or that direction, and then that gives you the refraction orders. And if that makes no sense, you don't worry about it. Just for those of you who've seen gradings, that's one way to think about it. Okay, so now you see where wave vector diagrams come from. This is worrying about the phase term there in the boundary condition. Okay, so now what we want to do is answer the question of how much. How much field, how much power. Any questions before I move on? We good? Okay. All right. So what we want to look at then is basically what's left here in this equation, but we still have the problem that we do not know what direction EI is in, or ER, or ET, and we really can't do anything else until we specify that. And so now what we're going to do is make use of one of the facts that we developed when we were doing polarization. And that is, if I have some polarization state coming in here, we know that in general it's going to be elliptical. And so we also know that any arbitrary polarization state can be decomposed into a weighted sum of orthogonal states. So let's make use of that. Let's say that whatever this polarization state is, let's break it up into a component that is orthogonal to the plane of instance and a component that is in the plane of instance. And why we're going to do that will be apparent shortly. But basically, it turns out those two linear states are eigenstates of reflection. And if we come in out of the plane, it stays out of the plane when we reflect and we transmit. If we come in the plane, it stays in the plane when we reflect and we transmit. So let's consider the case of out of the plane first. So we're taking any arbitrary polarization state, we're going to decompose it to out of the plane and in the plane, deal with each of them separately, add them up at the end. So if we understand these two cases, out of plane and in plane, then any polarization state is pretty trivial to deal with. Okay, so the out of plane case, this is also called TE for transverse electric. We'll see what that means in a minute. It's also called S, the S state. S is for senkrecht, which is a German word meaning perpendicular. It's also sometimes superscripted with a little perpendicular symbol. And what we mean by that is if we redraw our boundary between two media, 1 and 2, then what we're saying, so this is the z-axis, x-axis, and y-axis is out of the board. What we're saying is that this instant wave vector, ki, the electric field associated with it is transverse to the plane of instance, meaning that that electric field is out of the plane of the board. So, so that then would be EI. And so this is instant at an angle theta 1. And we know that the reflected light will be also at an angle theta 1. And then we have a choice here. We could assume that that reflected field is out of the plane of the board. We could assume it's into the plane of the board. But let's just assume it's out of the plane of the board. we're gonna explore that thoroughly. Because the reason why is because people often get tripped up over the ramifications of this choice, and I don't want you to ever get tripped up over it. Okay, so, and then we have the transmitted wave vector. We're going to assume that the transmitted field is out of the plane of the wave.
So when you're saying it's out of the plane, isn't it also, since it's propagating, right? You're saying the amplitude from
Mm-hmm.
so then it also goes into the plane, doesn't it? When it,
It goes into the plane
is it propagating?
as it oscillates,
Okay, through time.
but we're only looking at this piece.
Oh,
We've already taken care of all that stuff.
okay.
Yeah. And you'll see how it works out. Okay, so in other words, what we're saying is that EI is in the y-hat direction, ER is in the y-hat direction, and EZ is in the y-hat direction.
ET.
Oh, thank you, ET, perfect. ET. Okay. So that makes our boundary condition pretty simple. Our boundary condition is that EI plus ER has to be equal to ET. And notice how I'm using the notation. The vector, I'm talking about one thing. The non-vector, I'm talking about something else. So when I put the vector sign over, I'm talking about this whole thing. When I don't put the vector sign over, I'm just talking about the amplitude of that vector.
I feel it's the same thing in this case because they're all in the same direction.
This is why I'm bringing it up.
Okay.
You've heard me say that you need to be extremely careful to always indicate vectors as vector quantities, matrices as matrix quantities, scalars, as such. If you ever take a vector quantity and write it with no vector sign, you're being very sloppy, and that sloppiness often leads to errors, not only in execution, but also in understanding. So this is why I'm bringing this up. So when I stick a vector there, I mean this right here, that constant complex vector in this complex representation of the electric field. When I have no vector on it, what I mean is the amplitude or magnitude of that thing, which is not the same thing. They're related, sure, but they're not the same thing. Okay. All right, so we've got a boundary condition. Voila. Nice and easy. Now, there's another boundary condition, though. This is a propagating electromagnetic field. We haven't talked about the magnetic field yet. But we also have the boundary condition that the tangential magnetic field is continuous across the boundary. So let's make use of that, because we're going to need it. So,
I have just one question.
yeah.
This boundary condition that you have circle, it seems to me like you're creating E field in the transmitted area. Because if EI and ER are both positive, then ET is much larger.
Yeah. This is a really good point. Hold that thought. Yeah, no, that's a great point. We want to see exactly how that works out. Yeah, and it works out quite interestingly, and it's important to see how it works out. So yeah, good question. Hold that thought.
Okay.
Okay, so let's deal with the magnetic field. Put on the boundary conditions, and then we'll solve it all and see how that works out. Then we're going to have to do it for the TM case. Do the same thing, solve it, see how it works out. And then we can start making some statements about how things work. Okay, so first of all, we know that K cross E is equal to omega mu naught H. Right? From the Maxwell equations, when you substitute in, this is Faraday's law, when you substitute in for a plane wave, this is how it works out. And so all this is saying is that H is perpendicular to both the propagation direction, K, and the electric field. So if I stick my pointer finger of my right hand in the direction of K, and my next finger in the direction of E, then my thumb's going to be in the direction of the magnetic field. So that means that this is the direction of H sub I. If I do that up here, then I have that H sub R is in that direction, and H sub T is in that direction. Okay. So, what we want to do now is,
Excuse me.
yeah.
How you see that the direction of HT should be to the downward instead?
because of this, so this finger in KT, this finger in ET, then my thumb is in HT. Yeah, for the cross product. Okay, so now what we need to do is write down the boundary condition on the magnetic field. And the boundary condition on the magnetic field is that the tangential component, total tangential component on the left side is equal to total tangential component on the right side. So what is the tangential component of HI? What's that?
Gaussian triangle.
Yeah, so, yeah, so it's basically this piece right here, right?
Yeah.
That piece. If that's theta 1, that's theta 1, right?
Yeah.
I mean, you can see that by, if you go this way, then this is going that way, so yeah, it's both theta 1. Okay, so what's the component in that direction?
HA cosine theta.
So minus HI cosine theta 1. Right? Because it's in the negative x direction. Okay, so up here, what's the, this is theta 1 again. What's that component?
And how is the theta 1?
If this angle is theta 1, this angle is theta 1.
Just parallel lines and then cross. And the angles are equal.
Yeah. Yeah. So what's the x component of HR?
Cosine of theta 1.
Yeah, so plus HR cosine of theta 1. Okay? And that has to be equal to the x component of HT, so what's the x component of HT?
Sine of
H minus cosine theta 2.
Yeah, minus HT cosine of theta 2. Because this is theta 2. So that is theta 2. Are we good with it? Carlos, are we good with it?
Yeah, I'm just curious with the minus signs. It's just because of the direction?
Yeah, it's just the direction of the vector. Yeah. And that direction comes out because this has to be true. So we satisfy Faraday's law. Okay, so that's good. Now, recall that the magnitude of the electric field is equal to the impedance of the medium times the magnitude of the magnetic field. Therefore, the magnitude of the magnetic field is the magnitude of the electric field divided by the impedance of the medium. So I can take this boundary condition, rewrite it as minus E sub I over eta 1 cosine theta 1 plus E sub R over eta 1 cosine theta 1 is equal to minus e sub t over eta 2 cosine theta 2. So I've just rewritten the magnetic field boundary condition in terms of the amplitude of the electric field.
Quick question.
Mm-hmm.
Should H be a vector there?
No, so here's what I said. The magnitude of the electric field is equal to the impedance of the medium times the magnitude of the H field. So what do I mean by H there?
Yeah, the magnetic
The,
field.
the magnitude of the magnetic field.
You have a bar
Yeah, you have a bar
Two
on.
bars on the side and one on top would make it.
2 bars on where?
up on the
In that very bottom equation.
Oh, thank you.
Okay.
Thank you. Perfect. You'll find I have typos. So yeah, thank you for pointing those out. I really appreciate that. Okay, so this then is our other boundary condition. So we've got boundary condition 1, boundary condition 2. So we've got 2 equations. That means we can solve for 2 things. And what 2 things can we solve for? Well, the interesting thing is, if we solve for the ratio of the magnitude of the reflected over the magnitude of the incident field, and the ratio of the magnitude of the transmitted field over the magnitude of the incident field. So this magnitude we'll call little r, this ratio rather, little r, this ratio we'll call little t. So let's solve these 2 equations for those 2 ratios. And after doing some algebra, what we end up with is that this ratio r, and notice this is for the TE case, or the S case, or the perpendicular case. I'm going to subscript with S, just to remind ourselves this is TE. So we solve, and what we get is n1 cosine theta 1 minus n2 cosine theta 2 over n1 cosine theta 1 plus n2 cosine theta 2. So you notice the terms in the numerator and denominator are the same. In the numerator, we just have a minus sign. Denominator, we have a plus sign. And solving for t, what we get is Ts is equal to 2n1 cosine theta 1 over n1 cosine theta 1 plus n2 cosine theta 2.
Sorry, I think I missed this. What does the subscript S represent?
S,
Oh,
T,
right.
yeah. Yep. Okay, so, in other words, for the TE polarization case, we now know the reflection and transmission coefficients that relate the reflected and transmitted fields to the incident fields. So we just answered this question for the TE case. Okay. We're feeling a sense of accomplishment? And by the way, these are 2 of the so-called Fresnel equations. So now we need to turn our attention
What equation?
Fresnel equations. So Fresnel. 2 of the 4 Fresnel equations. Now we're going to get the other 2. So if we do now the in-plane polarization, which is called TM, so transverse magnetic field, also called P polarization, also sometimes subscripted with a little parallel symbol. Then, in setting up the problem with our z and x axes, we have the incident wave vector at an angle theta 1, the reflected wave vector at an angle theta 1, and the transmitted wave vector at an angle theta 2. then if we put the magnetic field vector HI out of the plane of the board, then because with Ampere's law for a plane wave we have K cross H is equal to minus omega epsilon naught E. If H is out of the plane of the board and K is in the plane of the board, my thumb goes this way, but we've got a minus sign, so that means that EI is in that direction. You good with that?
Can you do one more?
Yeah. So we've got K, and then this finger is in H, so E goes this way, but it's a minus sign, so we flip it, and now it's going that way. Okay. So then let's say that HR, let's just say it's coming out of the plane of the board. I mean, we could choose it into the plane of the board, but let's choose it out. Then following the same process, we get ER pointed that way. And then HT, let's choose out of the plane of the board. And then we have ET pointed in that direction. Okay. So we're good with that? That's our picture. Now we need to play the same game, do the magnetic and electric field boundary conditions. So let's do the magnetic boundary conditions first, just because they're simple. So we have that HI is equal to the magnitude HI times y hat, and HR is equal to the magnitude HR y hat, and HZ is equal to the magnitude HZ y hat.
HT.
Oh, T, thank you. Keep putting the Z's there. Okay. Then the electromagnetic, or the boundary condition for the transverse magnetic field is that it has to be continuous across the boundary. So we have that HI plus HR has to be equal to HT. And then we go back to this fact that H, the magnitude of the electric field, is equal to the magnitude of the electric field divided by the impedance. So this we'll rewrite as E sub I over A to 1 plus E sub R over A to 1 is equal to E sub T over A to 2, and that's one of our boundary conditions. Boundary condition for the transverse magnetic field. So, got that boundary condition. And then over here, let's write down the boundary condition for the electric field. So the transverse component is going to be basically this piece right here. So how much is that? Pardon?
Is it also theta 1?
Yeah, this is also theta 1.
Sine of theta 1 is
Sine of theta 1 is that guy. That's cosine of theta 1. Okay, so we have EI cosine theta 1. That's the fraction of this that's in this direction. And then over here, we want this much of it. So what's that? So this would be sine right here. This is the cosine part. Yeah, so minus ER cosine theta 1. So that's the total tangential electric field on the left-hand side. And on the right-hand side, what's it going to be? It's this piece right here. Okay, so positive ET cosine theta 2. Okay, so that's our second boundary condition. namely on the transverse electric field. Okay, so we've got two equations, now two unknowns. We'll solve for, again, these ratios, but these are the ratios for the TM case. So once we do the algebra, what we find is that R, and now I'll use the P subscript to indicate transverse magnetic. What we have is that the reflection coefficient is N2 cosine theta 1 minus N1 cosine theta 2 over the same terms, but now just plus sign, N2 cosine theta 1 plus N1 cosine theta 2, and TP is equal to 2N1 cosine theta 1 over, same denominator as for RP, N2 cosine theta 1 plus N1 cosine theta 2. And those are our other two Fresnel equations. So these are our Fresnel equations. And we've now answered this question for the TM case. And all of that fell out of just line boundary conditions. So any questions? We're good? We're loving it? Okay. Okay, so now what we want to do, oh, and by the way, as an exercise to the reader, if I multiplied top and bottom by omega over C here, it turns out RS would be K sub I x minus K sub T x over K sub I x plus K sub T x. So I could take the Fresnel equations and cast them in terms of the x component of the wave vector. But I'm not going to emphasize that. But you could do it. Sometimes that's useful. And you could use Snell's law, the law of refraction, reflection rather, to rewrite the equations in other forms. But I'm not going to worry about it.
So Snell's law gives us the direction, and Fresnel's equations give us the power. The fields.
Fields. Now we're going to do power. So this is, we want to finish our set of questions by looking at power. So that's what we need to do next. So let's consider, let's take this plane, and now I'm going to draw it, attempt sort of a three-dimensional drawing, and this is that plane. So we're kind of looking at it in perspective. And let's say I have a beam like this, and it's incident on this plane. And it's going to have a footprint that's kind of oval shaped or something. If this is circular, it's kind of oval shaped. And let's say that this irradiance is I sub I, so power per unit area. And this is coming in at an angle theta 1. Then we'll have some reflected light off like this at an angle theta 1. And then we can look at the irradiance I sub R that's reflected. And then we'll have some transmitted light here with some irradiance IT. And this illuminated area, let's say, has area A. So the question is, first of all, how much power is incident on the area A? So we could call that P sub I, that's the instant power. And all we know is the irradiance I sub I. So how much instant power do I have instant on area A? Ah, is that right? IA times A, is that right? Is A perpendicular to this direction? No.
Would it be like, cosine theta 1?
Yes, cosine of theta 1. In other words, we have to take A and we have to project it perpendicular to the direction the beam's coming. And so projecting it perpendicular, that's a cosine theta term.
Cosine theta 2, should we draw that in there?
Yes, yes, thank you. Absolutely right. Thank you too. Okay, so now what about the reflected power? What is that in terms of the reflected irradiance?
IRA cosine theta 1.
Yep. IRA cosine theta 1. Okay, so now let's define R, capital R, as the reflected power to the instant power. Then we can clearly just substitute in, and we'll have, yeah, we'll have this. And clearly those cancel, right? Oh, I got it backwards. Yeah. And then I can substitute in for the irradiance. The irradiance of the reflected is going to be magnitude squared of the magnitude of the reflected field divided by 2 times eta 1. And similarly, for the incident, eta 1. Right, we're good with that?
Yeah.
Okay, and the 2 times eta 1 cancels. And that leaves us with ER, magnitude squared, over EI, magnitude squared. And if I go back to my definition over here, that ratio is just the reflection coefficient. So this is magnitude squared of the reflection coefficient. So the power ratio for reflection is the magnitude squared of the reflection coefficient. The reflection coefficient relates the fields. And we call this quantity the reflectance. So that's the key result there. Now we could do the same thing for the transmitted power. E sub t is I sub t A
Cosine theta 2.
cosine theta 2. So we could define a transmittance PT over PI, and go through the same process, and I have IRA, or rather IT, A, cosine of theta 2 over II, A, cosine of theta 1. The A's cancel, but the cosines don't cancel. And now I can substitute in for IT and II. So I have a cosine theta 2 out front over a cosine theta 1. And then I have an ET squared over 2 times
Eta 2. Eta 2.
eta 2 over EI squared over 2 times eta 1. And eta 1 is eta naught over N1. Eta 2 is eta naught over N2. So when I substitute in eta naught over n1 here, eta naught over n2 there, the eta naughts are going to cancel. And let's cancel out these 2's. And what I end up with is n2 cosine theta 2 over n1 cosine theta 1 et magnitude squared over ei magnitude squared. And then substituting in for this, given that transmission coefficient, what I have is n2 cosine theta 2 over n1 cosine theta 1 magnitude squared of t. So that is our transmittance. So notice the transmittance is not just the magnitude squared of the transmission coefficient. We also have that factor of, yeah, it's basically a geometric factor. Okay. So now we just answered this question. Power. We know the fraction of the instant power that gets reflected, that's just the reflectance, and transmitted, that's just the transmittance. And we must have that reflectance plus transmittance is 1 for power conservation. And notice I've slid something by you. What have I slid by you?
No signs.
No signs?
Signs.
Well, over here we did everything in terms of out of plane and in plane polarizations. We broke them up. But we didn't say anything about that over here. So our reflection coefficient here, we have either RS or RP depending upon which polarization state we have. So technically, we should say probably reflectance for the S state is the square of the reflection coefficient for the S state. Reflection for the P state or TM state is R sub P squared. And likewise for TS and TP, etc. Yeah.
So if we had a TEM wave, then we would have two reflectances and two transmittances.
Okay, well, two responses. One, remember TEM wave, we use that to mean something very specific. And the specific thing we meant was transverse electromagnetic wave, meaning that for a plane wave, the electric field is orthogonal to the direction of propagation.
Mm-hmm.
So when we say TEM wave, really all we're saying is plane wave in the electromagnetic model. So I wouldn't say TEM wave. Instead, what I would say is if we have some arbitrary polarization state, we break it up into the TE and TM components,
Mm-hmm.
and then each of those we can treat individually, and then sum them up.
Okay.
Yeah.
So then TM is parallel to the boundaries.
TM is transverse magnetic, meaning the magnetic field is perpendicular or transverse to the plane of instance.
Okay, then electrical field is in the parallel.
And then electrical field then, because of that, is in the plane of instance. So that's what we need. Okay. So mission accomplished. We've answered our questions. Now what we want to do is know what the heck does all this mean? What are the practical ramifications of all this? And since we're out of time, we'll pick that up next time. And basically what we're going to do is, first of all, take normal instance, meaning theta 1 is 0. See what happens with normal instance. And then we'll do the general case of off-normal instance, and we'll find some other interesting things that happen. When we do normal instance, what we're going to do is see the ramification of our assumptions of ER and ET coming out of the plane, and HR and HT coming out of the plane. It's going to cause a little problem. It's really not a problem. But because what we've done, everything is self-consistent, it all works out in the wash. But I want to point out the thing that you could stumble on, just so you never stumble on it, which gets back to your question. Okay, also next week I've got to travel, but I arranged it so that I'll be leaving Tuesday afternoon after this class. I'll get back Wednesday night, so I'll be here for Thursday. So I didn't want to miss class, because we still have one class we need to figure out when we're making it up. But at any rate, so I'll be gone in between classes, but I'll be here for classes. Okay, well, looks like we're out of time, so have fun. We'll see you Thursday.